Hey guys, here in this lecture, we're gonna move to the section 25.5, talking about the electromagnetic waves. Just gonna give some briefly introductory for what the electromagnetic waves. Okay. So generally, I will start with what the graphical representation for the wave, and then what the main terminology that we need to know about any wave. So generally speaking, the wave, it has the shape of what we call sinusoidal wave. And that sinusoidal wave has certain element we want to list it in a second. But mainly thing we're gonna say, we call this one is the aperiodic signals. What that mean is the signal shape itself repeat themselves at a certain time. So in this example here, if I start from this point and at this point, then the signal come back to repeat themselves in the same way. So the first parameter that we're gonna learn about the wavelength. What the wavelength is. The wavelength is, it is just the distance between the two crests or two clouds. So either way, it's gonna be that's lambda. That lambda as a unit is the meters. Again, for the X and Y, that's represent the signal. It could be current wave, with amps, or the magnetic field waves or voltage wave. So, but basically most of the time, axis domain will be time domain. Okay, so that's the wavelength. The second parameter is here beside this one, the amplitude, or what we call the amplitude A, which sometimes we call it V peak or the peak value. So the peak value comes from the center to the peak of the wave. So that we call it V peak, or the amplitude is the highest of the wave from the midpoint, and is unit of the wave. If it's the current, will be amps. If it's volts, it's going to be volt. If magnetic field will be Tesla. Okay. So the third one we're going to talk about, it is the frequency. What about the frequency here? The frequency is the number of the wave, the crest that passed per second. So here is the regarding for that case, and what the regarding for this one, which is supposed to be this one is lambda, as you will listen later. But generally speaking, this is when we call it the, if we're talking about the time domain, we call it the period time. This is the period time. So the relation between the frequency and the hertz for the frequency, F most of the time will be 1/T, whereas the T, we call it this one period time, which the time the signal repeat itself after that time. The last terminology we're gonna talking about the speed. The speed, how fast the wave is moving. And as a formula, it is lambda multiplied by the frequency. If you use the unit, meters multiplied by 1 over the time will be meter per second. How much speed it will be. Okay, so that's the thing you're gonna, as a graphical representation for a signal. Now let's see talking about the some examples here, just to confirm those names. So the first one, they ask you to what the shortest wavelet. So we're gonna decide what the wavelet for every single. So this is one, the lambda A, and the same one for the B or C, sorry. And it seems to be it is the same. And for the B, between two crests, this is lambda, and this is one lambda for D. So basically, they ask for the shortest. So the short one will be B. It is a short one. Regarding for the ask for the amplitude, so it's very obvious it is D. How we found the magnitude? Basically, draw the line in the center, and this is the magnitude we are talking about. This is value. This is the magnitude we're comparing with the other A and B and C. You will find this is one is larger than O. So the largest one will be D. Now we're gonna introduce the electromagnetic waves. From the name, electromagnetic wave means I have electrical wave and magnetic wave and combined together to generate electromagnetic wave. And to get that concept, but let's go back a little bit for when you're talking about the Lenz's law, and we saw this example before, and we have here is the loop, and they are totally isolated from the wire. It doesn't touch the wire itself. And you remember, where according for the Lenz's law, we found that even this wire or this loop untouched the magnetic field, still we find the induced current. And it is, wait a minute, that's something is strange with that case. Even if the magnetic field untouched the wires, I am able to find the induced current, where the induced current came from. So if you just a minute, imagine we forget about the loop itself. Okay? It's talking about the magnetic or electric magnetic field. So when you have electromagnetic field, that's what generates the current. So basically, the starting point, when I have magnetic field and the flux, it changed. That's as a condition to generate the induced current. It's gonna be changed. And according for this one, that's the electrical field originally. And if you just look at the picture more, that magnetic field, when I have magnetic field change, it's gonna be generate a loop of electrical field. And that loop, it is the entire is around it. And the magnitude, as we mentioned in the beginning of the semesters, as close to this point, gonna be decrease and decrease, and but they have that directions. Okay. Now, if you put the loop again, and now you imagine, okay, now we have the loop. So basically the loop, it is already come in the field or on the range of the electrical field. So from the electrical field, generate induced current. So even though the loop untouched the magnetic field, it is touched based in the electrical field. So that's why two combinations, basically what I have magnetic field and I have electrical field at the same time, as I have the wave. So now regarding for the half the wave, so electromagnetic waves, basically it just combines the electrical wave with the magnetisms, the two theories together. And the two theories together generate a magnetic field, or the electromagnetic waves with the electrical field and magnetic field will be a change. And Maxwell's, he calculated something very, very interesting. One, how to find the speed, to give you the wave with the speed, and depend about the epsilon and epsilon zero and mu zero. Just to go back to beginning of the semesters, we have the mu zero. It is just 8.85 power to the minus 12. As a unit will be Coulomb square divided by Newton meter square. Newton multiplied by meter square. And the epsilon mu naught, so we have this one 1.26 power to the minus 6. As the unit, it will be Tesla meter square divided by ampere. So if you plug those numbers here and root square, you end up with the 3 power to the 8 meter per second. And in that time, the Maxwell time, we know that number it is equal to the speed of light. So basically what we have in the electromagnetic wave, it is the wave traveling with the speed of light. Another fact for the electromagnetic wave, the ratio as well for the amplitude for the electrical field and magnetic field, it is constant equal the speed of the light as well, which that basically what that indicated too, all the time, electromagnetic field, it has a value larger than magnetic field. So another thing here is the electromagnetic wave can exist at any wavelength, as we will see in next common lectures. We'll see the spectrum, and in the vacuum, all the light travel at the same speed. So now we need to see how the wave itself, how to represent. It's basically we have the electrical wave, electromagnetic wave goes upside down, and the magnetic field goes right to left. And as a representations, here is the electrical field with the magnetic field, they are perpendiculars, and the direction of the wave, it will be the same direction of how to the wave will be changed. Again, so at any certain point, the ratio for the electrical field and magnetic field, you can calculate it based on those values. So if you have, for example, this one, I'm still able to find the ratio equal C. Now here's the quick simulations about how the wave travel itself. If you look at one by the isolating here, it changed the magnitude and the electrical field at the same time, with they are perpendiculars and they are traveling. That's the same way to traveling. So this is when the travel for your signal. If you look at the signal comes this way, that's the same way of the traveling. That's the directions. But all of them should be perpendicular for those three regions. That's the electromagnetic wave in basic IB.